Hello, students. In the last unit, the kinematics, we talked about scalars and vectors, but we didn't dive too deeply into the subject matter. What we're going to do in this unit is we're going to dive in to what scalars and vectors are, and we're going to look at the mathematics involved with determining what is called resultant vectors. All right, so let's do a quick review. When we're looking at different types of scalar quantities, a couple different types of scalar quantities might be where you're looking at the temperature inside of a room. There's no direction associated with it, but we can see on the scale that we're looking at approximately 58 degrees Fahrenheit. There's no north, south, east, or west with that. When we're looking at the height of the yellow box, the height of the yellow box tells you how many centimeters tall that is. If we're looking at the triple beam balance and we're trying to measure up the mass of an object, when we have 1 kilogram, there's no direction associated with this. We don't say that it's 1.5 or 1 kilogram to the north, or we don't say that it's 2.3 centimeters to the south. It's just a quantity. Here, this is another good example. If you go to eat a candy bar, and you see on the side of the candy bar it has 300 dietary calories. Does that indicate the cardinal direction that it's going to be 300 calories to the west? No. So the key here is that when we're talking about all of these examples that I gave to you, not a single one of them has distance associated with it. It's not in there. There's no direction with these, okay? Now what we're going to do is we're going to move on to vector quantities. And vector quantities, they have direction associated with them. All right, so a vector quantity, what is the definition for this? A vector quantity has both magnitude and direction. So let's look at a couple of examples of vector quantities. So our first example, let's use the purple arrow right in the center. The purple arrow in the center is pointing to the west, so that's our direction. We would say that this would be 0 degrees to the west because it's pointing due west. All right, we're going to put some brackets around this so that way we know that that is the direction part of our vector quantity. And then depending on how long that we draw the line, that's going to determine what the magnitude is. So let's say that this is 25 miles. So that's the magnitude for this. All right, since we have two things, we have magnitude and we have direction, that means that that is a vector quantity. Now, on the left-hand side, you have what's called a spring balance. Now, this spring balance, as soon as you put a weight on the end of this, what we have is the gravitational pull of the Earth is going to cause this weight to pull downwards on the spring. Now, that number, whatever the amount of mass that we put on that, that's going to cause the spring to lower to different heights. So if we have the spring balance and it lowers to this point right here, we would say that this thing would weigh 35 pounds, okay? Now, since it is directed downwards, we would have a little arrow down, or we would say down like this, all right, because there is a direction. So that's a vector quantity. Now, in science, we don't use the term pounds. Instead, what we use is we would use the term newtons. So that is for the next unit. The idea here, one thing you're going to notice with each of those two examples that I gave you, I always put the direction inside of brackets. So that's going to help to indicate that that's the second part of our vector quantity. Now, if we were to use that purple arrow again, and I were just to put a little line underneath this, and then I put down here hours, now we're looking at the vector quantity where we're describing the velocity. So down below, if we have identify which of the following are vectors. All right, so in our first example, I have 0.6 meters. There's no direction with it, so that's a scalar quantity. 9.8 meters per second squared, that's acceleration, and there is a direction downwards. So yeah, that's a vector quantity. We have 91%, no direction, not a vector. 12 seconds, no direction, so that's a scalar. 4 kilometer or kilowatt hours, that's going to be a scalar quantity. 13 hours, scalar quantity. 31 or 32.1 degrees Celsius, no direction, scalar quantity. But here you see that we have a direction with it, so that's to the left, so that's a vector quantity. All right, let's make this quicker. You have here, there's a direction associated with that number. There's a direction here with that one. And then lastly, we have a direction here with this one right. Now, each one of those, you're going to notice that there is a direction associated with them. All right, so that's what indicates that we're looking at a vector quantity. It's a little more information. Let's take a look at ways that we can describe distance, because when we're describing distance, as the example with the purple arrow, I said that we went 25 miles. So how is that different if we're just talking about distance in general instead of describing it in terms of position or displacement? So distance, what we have to remember is that distance is going to be the total length of the path traveled, and that's going to be regardless of direction. So if I say that I'm on the highway and I'm traveling 50 miles, yes, I'm traveling 50 miles, but because I'm not telling you the direction of motion, you don't know if I'm traveling east, south, north, or west. All right, we just represent that scalar quantity with the variable d. The next way that we can describe location is in terms of position. In terms of position, we're looking at the actual location of an object relative to a reference point. Now, this is going to be considered a vector quantity, because if we were going to describe how far you are away from your house right now, you might, depending on where you live, you might be 5 miles south of where your house is located at. So that would be describing the position of you relative to where you started this morning. All right. Or if you were to change our classroom and we go across the hall to Mr. Hall's room, if we were looking at that from my doorway, if that's our point of origin, our reference point, we're going to walk approximately 15 feet to the west. So once you got into Mr. Hall's room, you would have a position that would be 15 feet to the west of where you started. Now, the symbol that we're going to use for this is just a D, but since we are indicating that this is a vector quantity, we're just going to put a little arrow on the top so that way we know that we're talking about a directional change. Our third way that we can describe location is to use the term displacement. Now, displacement is going to be the change in position relative to a point of origin. Now, you, this morning when you got up, and again, let's just pretend that you live 5 miles from the school. When you left the school, your point of origin was your house. That's your 0, all right? So we're going to say that if this right here is your house, all right, and you live 5 miles away from the high school, all right, so right here is the high school, that means that you would have had a displacement to the east in this case of, I said 5 miles, didn't I? Of 5 miles. Now, how would we determine that value? Well, if the point of origin is 0 meters, that's where you're starting out at, and the high school has a position 5 miles away from your house, your displacement then, when we figure out what the values are, you say that we are looking at a position 5 miles, subtracted from that what the original position was, 0 miles. We have a total displacement that would be 5 miles to the east of where you left your house. That was a very simplistic problem where we just had one change in position and it didn't even have any angle associated with that change of position. Let's look at an example where it's a little more involved, but it's not any more difficult. So we have Xavier travels to Yvonne's house And it says, how far does Xavier travel? Okay, so if Xavier starts at his point of origin right here, the X, and he travels 110 meters to the right, and then he travels 70 meters to the north, the total distance here that Xavier would have traveled would be the 110 meters plus the 70 meters. That's a pretty basic problem. There's no real difficult issues with that. What does that value represent? Well, that represents the total distance that they've traveled, all right, or that he has traveled. It says underneath this, it says, if Xavier was a bird, how could he get to his final destination? And what does this represent? Well, if we think of this as a bird flying from the point of origin, and we go in a straight line path like this line right here, this represents the displacement. All right, now remember, displacement is that vector quantity. It's a straight line path from our point of origin to the destination point. So this, another term that we use for displacement when we do a diagram like this, is the resultant. All right, so the resultant vector, the vector, because it has an arrow associated with it, we're going to figure out what that value actually is. Now this is going to involve two different methods. The first method we're going to use is to get the value, the magnitude of that black dashed resultant vector. All right, now we have formed a right triangle. If you have a right triangle, that means that you can use the Pythagorean theorem to get it. Now, everybody should have an idea of how you would finish this. If I say a squared plus b squared, you're going to tell me c squared. So if we label up our sides, we just say that this side right here is a, this right here is b, and this is c. It becomes a very easy problem to answer for the displacement magnitude. All right, to get the c by itself, you would have c equals the square root of 110 squared plus 70 squared. All right, we plug that into the calculator. Now I'm going to show you this because I want you to be able to plug this into the calculator correctly. You go square root, parentheses, you have 110 squared plus the 70 squared, close it up, and you should get, I have a little exclamation there. But if we did that correctly without the exclamation point, I don't even know what that is. That we should get 130 is what we should end up with. So we have 110 squared plus 70 squared. That's going to get you 130. All right, so that represents, that 130 represents the quantity for us to walk from this point over to that point right there. Now with every vector quantity, you have magnitude and direction. All right, we are going to spend a little more time on this, but I'm going to rush through this first one. What we want to do is we want to kind of think of this diagram right here, that wherever Xavier was standing at, we think of this as like his eyeball that he's going to be looking out of. All right, so if this is his eye right here and he's looking out, the side that is right opposite of his eyeball, I'm going to put the word opposite here, and the side that is adjacent to him, right next to him, I'm going to label this adjacent. All right, and then the longest part, we're going to label this hypotenuse. If I spelled that correctly, it doesn't matter. All right, what we are going to use is just a very basic small amount of trigonometry to figure out what that angle is. I know that this thing, in terms of the direction now, it's pointing to the northeast. But what exactly is this degree, this angle right here? All right. On your calculators, you have three trigonomic buttons that you can use. You have sine, cosine, and tangent, those three. All right. What we will use to solve this problem is we're going to use that tangent button. Now, tangent, and like I said, we will go over the details on how to use those trigonomic functions and which one to use and when. But for right now, I'm just going to walk you through it. What we're going to have is we're going to have our angle, this is theta here, equals the inverse tangent of our opposite side. That opposite side was 70. My adjacent side is 110. All right, so let's see what angle this actually comes out to be. Now, in your calculator, you're going to do quite a bit of this coming up. But what we'll do is first, I'm going to get rid of the E. Where am I even getting those at? All right, either way. We're going to go second function. See how I press the shift button and then my tangent has a -1 on there? We'll go 70 divided by 110, close it up, and my angle is actually going to be 32 point, let's round that off to 5. So it's going to be 32.5 degrees. That's going to be the actual angle here. So 32.5 degrees. So our resultant vector, the displacement in particular, if a bird was flying from Xavier's house to the destination, they would have to fly 130 meters at 32.5 degrees north off of the eastern direction. All right, does that make, hopefully that makes sense. If not, we will spend more time on that coming up. We have the last question on this side. It says a raceway is designed as a loop in which one lap is 40 kilometers. If a race car completes 200 laps, what is the distance traveled? Distance traveled, how far did they travel? Well, we know that one lap, all right, is 4.0 kilometers, but we are traveling around this 200 laps. So if we go times 200 laps like this, what we're going to end up with is a total of 800 kilometers. Now, what we're measuring here is the total distance. The second question, it says position at the end of the race relative to the starting point. Well, let's get a little graphic right here. If this is the raceway and I start right here and I stop at the finish line, if we're looking at the displacement now, then if I started and I stopped at the exact same point, what's my change in position? 0 kilometers. I'm at the same position that I started at, aren't I? And if I started and stopped at the exact same spot, my displacement then is also 0 kilometers. All right, so my change in position, we're looking at that distance, and then my displacement, my change in position, right there. All right.